So Thursday, we looked at intermolecular forces and how they contributed to a lot of different physical observables. You will likely see questions on the final based on your melting points and boiling points, which is ultimately how do we transition between phases. You will probably also see questions about solubility. And to a lesser extent, I'm not positive on this one, I think you might see a question on vapor pressure. But melting points and boiling points are big concepts. Solubility is a big concept as well. Okay? And I don't mean the solubility rules necessarily. I mean, given two compounds, two formulas, would we expect them to mix with each other or not? Okay? Which brings up a good point about the rules. I should mention this. I did go through the exams and highlighted or made note of the things that you absolutely needed to memorize. I posted all of that information. There should have been an announcement. Yes? Everybody see that? So you do have access to that. I don't think anything was actually outside of what we've already talked about. So I don't think it's that big of a difference from what you've seen from your previous exams. Okay? So review that. Make sure you're aware of what things you need to memorize. General rule of thumb, if anything stands out as something super different than what I've already told you to memorize, could be important. Okay? I did not go through and highlight everything that you need to memorize because that's a bit excessive. Okay? Like charge on a proton, charge on electrons, that kind of stuff. I didn't make note of that. Okay? So those are our interactions. We kind of pushed through solubility and then really kind of ended on this concept of what happens when we get to solutions. So when we dissolve something in water, we now have kind of a different situation than we've seen before. There are now two species present, the compound that we initially dissolved as well as water. And depending on the different circumstances, maybe water is involved in a reaction, maybe not. Okay? In all cases that you guys have seen this semester, all cases, I think that's true, water has never been a reactant. Okay? It is involved in the reaction, but only involved to the point where it dissolves the compounds. How do we know that it was in the or involved in said manner? It says aqueous, which means water is present. How do we know it's not involved in the reaction? Don't see water actually physically written there. Okay, so the aqueous implies the presence of water, and it's really there only to dissolve the species to help them interact with each other. They do not, or it does not form an exact role within the reaction. Okay? Which brings up an issue. When we move into the lab, we usually weigh things out. Okay? Or we could even take the volume of a substance. When we weigh out or take the volume of a solution, we're not getting the mass of just, say, aluminum bromide. Okay? What we'd be getting is the mass of aluminum bromide and water. So we can't just convert, like we would normally, the mass of our solution into moles of aluminum bromide to predict how much of a product would form. Likewise, if we took the volume, okay, well, the volume of that solution has a little bit of the aluminum bromide in it, but it has a lot of water in it. We don't know that exact volume differential, so we can't really use the volume to be able to use then density to calculate a mass, to then be able to convert to moles, to then be able to predict how much product we could make. All right? So we need a new relationship, some kind of conversion factor or way that we can quantify the amount of our reactants within these solutions. Okay? And that's what that question is then asking. Okay, that last one. How do we quantify our silver bromide? Well, the silver bromide was straightforward. Why is the silver bromide a straightforward quantity? Where is silver bromide? It's in the product and it's a solid. Why is that a straightforward quantity to quantify? It's a solid. We can separate it from the rest of the solution by filtration and we can weigh it. Okay, so that's relatively easy to find. But where did it come from? Well, it came from these two solutions. And it's not the water within those solutions that made silver bromide. It's the aluminum bromide and the silver nitrate. It's those compounds that made the silver bromide. So we need to know how much of those compounds were present. So ultimately what we have to determine is a concentration. How much of those compounds were in the water solution? Okay? To do that, we have to either, well, it doesn't matter what we have to do. We have to come up with a new unit or a new kind of conversion factor. Some way to relate the amount of that species in the volume of the solution. Okay? We have seen ways to represent this before. Okay? We could look at a volume of our solute to the volume of the solution. Okay? That's a percent by volume. Okay? That was done chapter 2, I think. We could do it by mass. We could say the mass of one compound per the mass of the solution. And we'd have a percent by mass. Percents can be a little bit confusing, and what makes them particularly more difficult is what are the units on percents? There isn't any. Okay? So that makes it more difficult to go through and do our conversions if we don't have a unit on which we can convert. Okay? So what we end up using instead is this our quantity or unit known as the molarity. Okay? It is a super commonly used term. You'll see it as a capital M. You've seen it throughout the lab. I've had students ask me about it throughout the lab this semester. And what was it now? 3 weeks ago, you actually did a lab where you had to calculate the molarity. And ultimately what it's doing is the same thing as all of our percent concepts are. We're taking the amount of a species in a larger solution. So it's the moles of whatever target substance we're concerned about in the liters of the entire solution. Okay? Or the entire solution where it came from. Okay? So we can use that to be able to convert back and forth between a mole value and a liter value. This means if I give you a volume of my aluminum bromide solution and a molarity, you can calculate the moles. Well, once you know the moles of the aluminum bromide, what could you do? You can now convert those into grams. You could also convert them into the moles of any other species using the balanced equation. Okay, going back to all the way to chapter 9. So what we're going through and doing is incorporating these new units and now making you do all of the same calculations again and again and again and really again and again and again. Right? There really isn't anything new on top of it. You just have to realize where these conversion factors are coming from and make sure you supply them and use them appropriately. Make sense? So let's do an example here. We're going to pick simple examples because these are going to be the ones you'll see on the exam, and I last second deleted a harder example that I think will be in your slides. Okay, what is the molarity of a solution containing 24.0 grams of sodium hydroxide and 0.1 liters of solution? Okay, what are we trying to solve for? Okay, molarity. Our symbol for molarity is a capital M. Okay? Really all that is a shorthand notation so that when we type it up and put it on a label, it's really easy to write. Okay? As far as you're concerned when trying to solve a problem, you should never write it out as capital M. Okay? Why? How many times have you seen capital M show up in any unit? Shows up once. And it only shows up when we're talking about molarity. Okay, so what we want to do is convert this M into a unit that makes more sense. What are the units on molarity? Moles over liter. So that's really what we're trying to solve for. Okay? Remember, whenever you attempt any problem, it's not just that base unit, the moles or the liters. It's the moles of what? What's the substance? You're right. In this case, it's NaOH, and this would be the liters of our solution. Okay? Taking that information, we can now start to put together our problem. Write down where we're trying to get, and I definitely didn't give myself enough space. Our moles of NaOH. for our liters of solution. Okay? So, what other information are we given? We are given 24.0 grams of NaOH. I put that in a straight line? That's pretty close. What unit do we want at the end? At the end, we want moles showing up, and ultimately we want molarity. We'll deal with the larity part of it in a second, or arity part of it in a second. Okay, so how do we convert our grams into moles? We're getting pretty good at that? What? Is that what I heard? Do we want grams showing up in our answer? No, which means that unit needs to show up where? Grams of NaOH on the bottom. Okay. What unit do we want to show up in the numerator? Have I mentioned anything about liters in this calculation yet? No. Not super important to mention it yet. We don't have to get both moles and liters in a single calculation. In fact, we won't be able to do that because we're starting with grams of NaOH. I cannot bring in the liters of solution if I only have grams of NaOH. So what we're doing is deciding which unit we can solve for first and setting up our work to approach that as best we can. Okay? Where do we find that conversion factor between grams and moles? Our periodic table, which tells us 40 grams of NaOH per 1 mole. Did I do that right? 39.998 is 40. Don't give me a hard time on that. Okay, so we're at 40 grams and 1 mole. What's our unit now? We now have moles of NaOH. So that gets us closer to our final unit, but we're not there perfectly. Okay, we now have moles, but I need to be divided by the volume of my solution, the liters. Do I have some more information in the problem? I'm given a volume. Where should that volume show up? Why in the bottom? That's where it is in our answer. Okay, so we need liters of solution on the bottom. The number that goes in front of that is our 0.100. What number shows up on top? Or what unit shows up on top? Okay. Kind of. And the way we've set up this problem, it is only 1. Okay? There are a couple other answers that got floated out there. What did you say, 0.6, 0.6 moles of NaOH? Where did you get that number? You did this first calculation first. Okay? So the approach that we just went through was solved for our molarity in one single step. Okay? Molarity, or these complex units, can be a little bit more difficult to solve for in one step, largely for that calculation shown in orange. Everybody looks at that and goes, I can't have no unit on top of or in my numerator. It just doesn't make any sense. Well, is that really true? If we can put 1 in the denominator, why can we not put 1 in the numerator? Okay, that is a perfectly valid thing to do. Okay? The other approach to this is saying, you know what, this complex unit is confusing. Really what I need are 2 pieces. The 2 pieces I need to solve for this would be my moles of NaOH, and the second piece would be my liters of solution. Okay, so instead of doing this in one single step, we break it into 2. What color? Yeah. So in our first step, what are we trying to solve for? Moles of NaOH. How do we solve for the moles of NaOH? What we had in red up there. So our 24.0 grams. Oh man, sorry, bear with me as I write this all out. 40 grams of NaOH is 1 mole of NaOH. And you said it was 0.6? 0.6 moles of NaOH. What's the second part of my calculation? What's the second part of the calculation? The liters. I need to solve for the liters of the solution. What is the liters of solution? Is it something I need to solve for? No, it's given to you at the very beginning of the question. It's 0.100 liters of the solution. The very last step, if we're going to break it down into this many sections, would be to solve for molarity. What is molarity? Moles over liters. What was our mole value? 0.6 moles divided by 0.100 liters. Okay, officially NaOH and solution. This gives us as an answer, if I did this right in my head, 6 molar NaOH. And we could write that down as our answer. Taking into consideration, of course, everybody's favorite, sig figs. Someone started to mumble it out there. It would be 6.00 molar Y. We go back to the numbers provided. We had 3 sig figs in each of our calculations.
Over liters? I thought you said with sig figs you don't have to worry about it unless the problem specifies it.
And so there's 2 places the problem can specify it. Okay? The first place the problem can specify it is in the question. Where's the second place the problem can specify it? In the answers. If in the answers you were given 6 molar and 6.00 molar, the answer is 6.00 molar. Okay? So there are 2 ways to show that. And why I said it's only going to get specified, or why you have to look for it in the question, is that if we are asking a question about sig figs, it says in the statement, in the question itself. Okay? Which is why I think when faculty complain about sig figs and make this big deal about it, it's not that big of a deal because you're asking for sig figs. Any point with any other calculation, the answers we give are not 6 and 6.00, but you'll see 6.00 molar, and then we'll change some other number. Maybe you multiplied by 40 when you did the calculation. Okay? The sig figs in this question would always come out as 3 sig figs. None of your answers are going to show anything else. So there are 2 ways you can see it. Sometimes in the answer choice, most times in the question. Okay? So back to the initial question all the way back here with trying to run it in one line. I did hear a couple people tell me that on top we should write 0.6. Okay? If we write 0.6 there, what are you saying? It says I take 24 times 0.6 divided by 40 divided by 0.1. Does that get you the correct answer? No. Okay? So your work may be incorrect. You might have gotten the correct answer. Okay? And this is something I want you to be aware of. If you put an equal sign, that means the calculations on the left equal the calculations on the right every single time. Most people, that is not the case. You aren't writing it mathematically correct. You're writing it for your ability to go through and solve, which is fine as long as you don't make a mistake. As soon as you make a mistake and try and check your work, you're not going to be able to follow your work because you're going to say x equals y, and that doesn't make any sense. Okay? So be careful with how you go through and solve. You really get 2 methods. Try and solve it in one big stab. I typically don't do that. For some reason, that was the first thing I went through. Okay? Or you can break it down into the individual parts. Look for the units that you're trying to solve for. Okay, in your complex unit situations, solve for each of those units independent, and then do whatever operations you have to get those units in the correct spaces. Okay, kind of makes sense? Okay, pretty sure we got a second example here. Yeah, second example. Now numbers we've got, the numbers that we start with, which number gives us a unit that comes closest to what we're aiming for our final answer? Okay. Moles of potassium dichromate. That gets us our potassium dichromate. Okay, that gets us half of our final answer. Our final answer needs to be grams of potassium dichromate. So this 0.15 moles of potassium dichromate at least gets us part way there. Realize it's not just moles of potassium dichromate, it's moles per liter. So we will still have to take that unit into consideration. Yes. Yep, which means moles per liter. Moles, what's our definition for molarity? The moles of the substance dissolved in the solution. What's our substance? Potassium dichromate. So that's moles of potassium dichromate in liter of that solution. It absolutely matches.
Does it have to be balanced? Would you put 125 milliliters underneath that?
No. No. The 125 milliliters, and so this is where we've got to, and you may be propagating your calculation further out. Okay, so let's continue and go through, and you may have condensed some of your calculations. Okay, so where I would start with, okay, is we want our 0.150 moles of our potassium dichromate on top, and our 1 liter of solution on the bottom. Okay, that gets our potassium dichromate in the numerator. Why did we want it in the numerator? Where does potassium dichromate show up in the answer? In the numerator. So when I go through to put in this conversion factor, where should my potassium chromate show up? It should show up in the numerator because that's where it needs to show up in the answer. Yeah? Okay. Now the question. Check your units. Do your units match? No. Okay, so now we get to decide. Okay, what unit do we want to fix first? Okay. I would probably argue that most people are more confident with the moles to grams conversion. Okay, so let's take a stab at trying to get that unit fixed. To do that, what do we need to do? We need moles of our potassium dichromate on the bottom, and we need to get rid of our grams, and get our grams of potassium dichromate on top. This way, when we go through and look at our unit conversion, our moles will cancel out, and we'll now have grams of potassium dichromate. So that's getting our unit closer to what we want. What's that relationship? Let me try that again. Where's that relationship found? On the periodic table. What is that relationship? Hopefully you guys calculated it. Never mind. What's that?
294.
Hopefully everybody got 294.2 grams per 1 mole. Okay. What's our unit now? I want to get you to change that a little bit. It's not grams over liters, it's grams of potassium dichromate over liters of the solution. So we're pretty close. We've got the gram unit fixed. That is exactly what we want in our answer. But we have this pesky liter unit showing up. Right? Which means we're going to have to do something to get rid of that liter unit. Okay? To do that, we're going to have to multiply by liters of solution. What should be under that? 1. Careful. Okay, we need to multiply by the liters of the solution. That cancels our liter unit, and we now end up with our grams. You notice that we're dividing it by 1. Okay, and this is why this conversion gets a little bit weird and people don't like this. Because we just put this random 1 underneath. Why is it 1? Because we need to maintain the volume. It needs to stay whatever that number is. Okay? Do we know the liters of the solution? We don't know the liters, we know the milliliters. Okay? Ultimately, what we're trying to do is cancel our volume unit, so we're multiplying by the volume. What's the volume unit we have? Milliliters. Do our units cancel? No. Which means, what are we going to need? We're going to need another conversion. That another conversion is going to have what unit on top? Liters, and what unit on the bottom? Milliliters. Okay, what happens to the units? Cancel out, and we'd be left with a final answer in grams. Okay. Some of you are able to convert milliliters to liters in your head and can put that number in directly here without having to do that extra conversion step. Okay. For those of you that think you can do that, please don't. I'm definitely still seeing a lot of people mistaking that conversion. Okay, so I'd like you to hopefully have something where you've got what that milliliter means, and you can write that conversion out, and you can get that conversion correct each time. Okay, so now let's adjust real quickly and deal with our numbers. What number shows up in front of milliliters? It's our 125.0 milliliters. If we go to our unit conversion, what numbers show up in front of our liters and milliliters? I'm sure I'm going to get a fistful of different answers here. The way we've been talking about it is that. There are other versions of it, as I'm sure you're seeing from the tutoring center, because this definitely wasn't a problem at the beginning of the semester, and we're starting to see it become a bigger issue. Okay. Milli meant 10 to the minus 3. So 1 milliliter, if that little m means 10 to the minus 3, means 10 to the minus 3 liters. Okay. Yes, there are other perfectly valid conversions. For those of you more comfortable with those other valid conversions, you could say 1 liter is 1,000 milliliters, or 10 to the third milliliters. As long as you do it correct, I don't care. Okay? But the way we've been talking about it, the way your book presents that material, is 10 to the minus 3 means that milli. Okay? We now can look at our calculation all the way through, and we get our correct units at the end. Are there all sorts of variations along this? Yes. You can break this calculation into individual steps. Okay? Where you wanted to, you actually wanted to divide by the 125, puts you in the wrong place, because what happens with our calculation? What did we have to do with the 125? You had to multiply. Okay? If you set the units out in front of you, your units will solve it for you. This 0.15 is moles per that liter of solution. That's what the unit of molarity meant. It did not mean that volume of solution. It meant that is the concentration of that solution. Of that solution, I took 125 milliliters. Now how much is in that 125 milliliters? Okay. This one becomes more challenging because you have to do that extra SI unit conversion as well. Okay. So this is probably the most challenging that you will see on the final. I think what you see on the final is similar more to the top one than the second one. Yes?
So the molarity one is super confusing too, because on the last one our answer was the calculated 0.6 over 0.100. So how do we know that 0.150 is moles over 1 liter?
It is always moles over 1 liter.
Yeah, but so this one.
So when your final answer.
6 moles over 1 liter.
6 moles over 1 liter.
Even though the calculation we used to get there was 0.6.
So you could report it as 0.6 moles over 0.1 liters.
Yeah.
When we report molarity, by definition, it is moles per 1 liter.
Per 1 liter.
Yep.
So if it's like any number
Any capital M means moles per 1 liter. That number represents the moles in 1 liter, which might be your 125 question, why you couldn't put the 125 in there. Okay? The molarity unit is always the number of moles in 1 liter of the solution. Every single time. We want to convert and get rid of those fractions so we don't have to worry about them later.
But it wouldn't technically be wrong to leave it.
So if your bank reported your income based solely on fractions, would you be particularly happy with that? No, it's going to confuse you. The reason why it could further confuse you, or not the reason why, but not only would it confuse you, but then the bank could potentially be stealing money from you because you're so confused about what money they're giving you that they can take money away from you really, really easily. So we always want to put it into as simple a unit as possible, which means get rid of the fractions, and if we could get rid of the decimals, we'd get rid of the decimals as well. But we want it as a single value in the numerator. Yes?
No, just to make sure, is the answer 5.52 grams?
Anybody calculate it?
Yeah.
So there we go. Everybody should be getting 5.52 grams. Okay. Based on the anonymous, or not anonymous, but whatever it was, democratic vote there, presumably everybody ran through these same calculations. You get the same thing?
Yes.
Okay, good. Okay. Yes.
On that third term where you have the one on the bottom, is that
Mhm.
only because we knew that the units were going to cancel 0? I don't understand anything of a 1 without a unit, and I don't know where the came from.
What's the number that you put on top?
125.
125 what?
No,
Per what?
one.
Per one sample. We took one sample of 125 milliliters. The unit on the bottom can't have a unit because then it's not 125 milliliters. And it can't be another number because then it's not 125. Remember, we always reduce it to that single value. Okay? Where you would typically see that 125 would be way out in front. So if you go back to every other unit conversion we've ever done, the first number we start with typically has 1 unit, and that 1 unit is in the numerator. Okay? We just decided to not start with that value. Okay, so it looks weird floating in the middle, but it is the exact same as if we'd put it anywhere else. Okay, questions about that? What's that?
I just like it in the front better.
I like it in the front better too, that's why I said that, but there's no unit comparison for you to solve. Okay? So next thing that we need to briefly, this takes forever to write out, but I'm going to do it anyway. When we looked at our reaction equations, particularly the double replacement reactions, okay, we get these nice simplified reactions. You can go through and balance them. Everything's nice and wonderful with the world. All of you, most of all of you are in my lab, and those of you that aren't in my lab, well, the one of you that isn't in my lab, probably ran into the same thing. When we did that single replacement reaction, how many times did you have to show nitrate? I know that's a stretch to remember. Oh, 3 of you that aren't in my lab. Okay. Typically, we stopped counting the nitrate when we looked at the single replacement reactions. Why do we not look at the nitrate? It didn't do anything. When we went through and did the copper ore lab, when you provided the balanced equation, it was copper ion plus aluminum to give you aluminum ion and copper. Okay, and copper ion and copper solid. Where was the compound in our single replacement reaction? We didn't show a compound. Why not? Well, because the ions were aqueous. We didn't care about what their other component was. All we were looking at is where the chemistry occurred. So when we go through and look at double replacements or sometimes even single replacements, what we end up doing is simplifying our equations. Instead of looking at the molecular format, which is nice because that balances things for us. Okay, so if you think all the way back to everybody's favorite balancing are redox reactions. Okay, as long as we had what's known as the counter ion, we didn't have to worry about it. The counter ions could balance and we could get everything figured out without having to look at charges, without having to look at oxidation states or electrons transferred. It was a lot easier. Okay? But what if I only care about the reaction? Only where the chemistry occurred. Okay, well, in that circumstance, I want to get rid of all the junk. To be able to get rid of all the junk, I have to know what the junk is. So what we're going to go through and do is take a closer look at this molecular format and start to break it down into individual species so that we can see it. What does aqueous mean? That it's dissolved in water. What kind of bond is there between aluminum and bromine? Ionic. I think you might have been saying. Okay, we've got an ionic bond. When we take sodium chloride and we put it into water, it dissolves, right? What happened when it dissolved? We got the individual ions, sodium ion and chloride ion. So instead of writing aluminum bromide as aluminum bromide aqueous, I can go through and say that, hey, it's in water, it's an ionic bond. That means it turns into the ions. So I get aluminum ion. How do I know it's a +3? Always a +3. It's one of the things you need to memorize. That aluminum ion is dissolved in water, so I have to specify that phase. Plus my bromide ion. What charge is my bromide ion? -1. Also dissolved in water, aqueous. But when aluminum bromide dissociates into the ions in water, is it just one aluminum and one bromide? What does that number mean? That means there are 3 of the atom immediately in front, which means when we now go to our total ionic format, where do we put that 3? We need to put it in front because it's representing 3 bromides, not Br3 as a complex ion. Okay, I know it's a little bit tricky, but you have to remember what each of those numbers meant. That number meant that we had 3 independent bromides. So if I separate it now into the ions, I'm going to get aluminum ion and 3 of those bromides. That 3 gets put out in front. What happens when I take a look at silver nitrate? I also see that aqueous. So now when I take a look at that, I go, well, that just means that I have silver ion that is dissolved in water. Oh, I hate this format. And I have nitrate ion, I don't know why I decided to cycle it there, or circle it there, dissolved in water. Is that a correct dissociation? Why do I translate that 3 down to after the oxygen? That 3 is just a part of the compound, or the formula nitrate, as the G is part of silver. So it does translate with that one. It's not looking at the quantity of nitrates, it's looking at the number of oxygens necessary to make nitrate, the complex ion. But I still need to put a 3 out in front. Well, we just said the 3 doesn't translate to in front, so why do I put a 3 in front? That 3 applies to everything after. So that means that there are also 3 silver. Okay? And this is where it's going to get kind of messy because I don't think I can fit the rest of it in this. Okay? Now we can shift to the other side of the reaction. Silver bromide. Yep, ionic bond. Common mistake. Let's split it into ions. Why do we not split silver bromide into the ions? It's not aqueous. It is the solid phase. You cannot touch it if it is solid. The only time it dissociates is if it is aqueous. So we're going to get, sorry, my screen just tweaked out. Silver bromide solid. How many of them did we have? 3. Must keep that number there. Okay? Followed by, what's the next species? Aluminum nitrate. Aqueous. Again, ionic bond. Again, aqueous, which means aluminum ion, aqueous, plus nitrate ion. Oh, man, I hate this one. Aqueous. How many aluminums are there? How many nitrates? 3. Horrible format because it takes up a ridiculous amount of space. Okay? But this is how we can then move to the net ionic format. Okay? Remember when we looked at electrons? I know everybody's favorite. When we looked at them in their reaction, we had to make sure they canceled out. Same number on each side. If we had the same number on each side, we could cancel them. We could simplify. So what we can go back and do is go back to our equation and say, you know what, I'm going to simplify. Aluminum ion, aqueous, Al plus 3. Does it show up as a reactant? Yes. Does it show up as a product? Yes, which means it's the exact same across both sides. I can cancel that term. Bromide, aqueous. Does that show up as in the product? I see bromide, but is it bromide aqueous? No. Right? In fact, I don't actually even see bromide. I see silver bromide. That's an entirely different species, which means I'm going to leave 3Br minus alone in the aqueous phase. What happens when we move to the next species? Silver ion. Do I see silver ion show up as a product? Nope, which means I'm going to leave it alone in my equation. How about nitrate ion? Shows up in both a reactant and a product. How many shows up on each side? 3 and 3, which means they can entirely cancel. I now moved my reaction arrow and write whatever's left over. 3 silver bromide solid. What we've now done is converted our molecular format into our net ionic format. In the net ionic, what we've now done is said there's a whole bunch of junk I don't want to look at. I just want to look at what is physically happening within the reaction. Everything else was just there to carry things through. Okay? So that simplifies what I have to write for an equation. Okay? Calling all the other stuff that we crossed out junk, kind of mean. We want to come up with a fancier name so they don't feel so left out. What name do we come up with? All the 3 of you that didn't have me in lab should be able to tell me. Spectator ions. Okay? Because they were spectators. They watched the reaction occur. Okay? So we've got those as spectator ions.
So is this kind of that one of the labs we did with hydrochloric acid in the common element? Is that, like if we did this, the hydrochloric acid would be canceled out?
Yep.
Okay.
Yep. Okay? So it's just a simple, or a way to simplify the chemistry down to only what we want to look at. That's all it ultimately is. Be aware that really all we're concerned about is a molecular format and the net ionic. The total ionic is really just the intermediary that allows us to get through it. Very rarely will you ever see questions about the total ionic format because, as you already saw, by my opinion of it, it's long, it's tedious to write out. Most people just don't like dealing with it. Okay? You kind of need it to be able to cancel the terms to get to the net ionic, yeah. So if you're asked for the net ionic, it's a bit obnoxious because you do have to go through the total ionic. Okay? When can you separate things into their ion states? Only when they are aqueous. If you see a solid, do not touch it. What if it's a liquid? Still not aqueous. Don't touch it. What if it's a gas? Still not aqueous. Don't touch it. Okay? Leave it as that compound. Do not adjust it thereafter.
Why only
It has to do with their dissolving processes. When we look at a salt dissolve in water, it separates into the ions. That's all it is. Yep. Okay? So we're going to kind of whip through probably the more important section in my opinion, but there's very few questions on it, looking at acids and bases. If we went through to name these compounds, that first one, we've got hydrogen disulfide. Nope, try that again. Dihydrogen sulfide. If we put an aqueous after it, what does it become? Hydrosulfuric acid. If we took a look at that last one, what is the name of that one? Sulfuric acid. Okay, binary acid versus a ternary acid, which brings up kind of the larger point. Why do these acids get special names? Okay. Right? It gets a different name because the chemistry is drastically different. We want something to recognize. So when chemistry was first budding up, we saw a couple different, what I would call observationalists, not really scientists, but just noticing certain different properties. So when you burn wood or burn different other things, if you take those ashes, they've got particular chemistry associated with them. They noticed some of that chemistry. They also noticed it in other compounds they found. Grapes that had fermented weirdly. They got this weird, bizarre flavor to them. They were able to extract that and kind of classify it. We really saw two big things: sour tasting and slippery feeling. Okay? Interesting phenomenon to see these kind of two separate categories. What kind of compound is sour tasting? Acids are sour tasting. That slippery feeling is a base. Allegedly what's happening when you feel that slippery feeling is the base is reacting with the fat in your skin and turning it into soap. And that's why you feel your fingers slip along each other when you touch bases, okay, or even when you touch soap. Okay? So what we're looking at is these new classes, acids and bases. Okay? Why do we separate these out as a separate category? What type of reaction do we have here? Two answers. Double replacement. So it's a standard double replacement, and yet we don't have any real ions happening in one of our products. Okay? We got a, what is that one? Covalent compound, okay, instead of an ionic bond. Interesting phenomenon. When we ran through and do these reactions, when we look at a double replacement, one of the things we look for, change in phase, okay, seeing a solid form. When we mixed an acid and a base, did we see a solid form? No, the only thing we saw was heat. That heat was a form of a reaction, but why did we not see the standard double replacement? That's because we were running a different reaction. That's why we call them or separate those out as a separate reaction. We look at them as neutralizations. Okay? So we've got these acids and bases generating this new type of reaction. We're done at 40, right? Good. So the first attempt at a definition, probably by Arrhenius, or at least the one that picks up this. Okay? So what he went through and did is took some of these sour-tasting species, dissolved them in water, and he was somehow able to note that those species generated hydrogen ion when they hit water. Okay? So he said, aha, my sour-tasting species, I'm going to call acids, and they increase the concentration of hydrogen ion in solution. Cool. He then also went through and took some of those slippery feeling compounds, dissolved them in water, and was able to note that he saw an increase in the concentration of hydroxide ions. So he said those were bases. So it's a good first pass as far as a definition goes, but we've got some pretty big issues with it. It really is a very, 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 very narrow definition, to the point where it's so specific that we can't really use it in real-world chemistry. So I like to call the definition useless. Okay? It is one that definitely shows up. It's just not that important. Okay? It's strictly a, here's a definition, memorize it kind of thing. Okay? You can't really apply it very well. Later on, we refined those definitions, and we came up with two ones. Sorry for all the erasing. This is why you look at the slides. Two more definitions came out. The most important one that you're going to deal with is the Bronsted-Lowry definition. Okay? And what they went through and did is, instead of looking at hydrogen ion and hydroxide ion, they said really what's happening is that we're looking at the hydrogen ion being transferred around. Okay? So they stuck with the definition for an acid being a hydrogen ion donor. Okay? So that definitely still holds true. So that's still an acid. Okay? But when they looked at the base, they said it's not just that it gives off hydroxide, but really that what it does is it accepts that hydrogen ion from an acid. Or it takes that hydrogen ion away from something else. So it's a very subtle change in the definition, but it opens up a lot more potential chemistries. So for your lab assignment, the one on double replacements, if you go back and take a look at those predict which of these reactions occurred, several of them were neutralization reactions. Okay? At least in my class I said that was fine. You can say those were no reactions because I didn't think you had the abilities to look at those yet. Okay? Go back and take a closer look. You'll find that a lot of them were acid-base reactions. Those were actually reactions you should have predicted products with them. Okay? So when we look at these, they're always exothermic. 90% of the time, we're looking at the production of water and a salt. Right? The salt is coming from your standard double replacement reaction. The water is coming from the neutralization aspect. We're neutralizing that acid with that base. Right? So our Bronsted definition allows us to apply in things that don't necessarily give up hydroxide ion, but do still accept hydrogens from acids. The most common example that you'll see, ammonia. Ammonia can react with hydrogen by sharing its electrons. Okay, we've got that lone pair of electrons on that nitrogen. If we react that with H+, we can make ammonium NH4, with our nitrogen being positive. Okay? Still an acid-base reaction, but we don't see hydroxide involved in that reaction. So this definition is a little bit broader, a little bit better. Turns out there's an even better one, which you'll see in organic chemistry if you move there. Lewis acids and bases. What do we see, or where did we see Lewis before? Making structures using what? Dots. What were our dots? Electrons. When we look at the Lewis theory of acids and bases, what is he looking at moving? It's the motion of electrons. Okay? You should be able to derive those if you're interested enough in it, or I can talk to you after class about it. Not important enough for this class. Okay? The next part is taking a look at some reactions. There are some species that are kind of interesting in the respect that they can act both as acids and bases. Those are known as amphoteric compounds. Again, such a subtle thing, not that big of a deal. But we can bring in this idea of conjugate partners. Okay? So if we take a look at that first reaction, okay, let's put down some definitions. I'm going to label that one as an acid. Okay? Why is this nice? Because if I know that's an acid, what does water need to act as? A base. What do acids do? I know the definition was just a few slides ago. Donate hydrogen ions. So what do we need to do? We need to get rid of H+. Okay? Take that away from that structure. If we get rid of H+, what do we make? Well, I lied. Let me get that arrow up there first. We need to lose that H+. What does the base do? It needs to accept that H+. Okay? So with those definitions, what can we now do? We can predict the product. If HSO3- loses H+, what does it become? SO3 minus 2, because it lost that H+. It lost that positive charge. What happened to H2O? It gained a hydrogen ion. So now its formula should be H3O+. Okay? Kind of neat. Okay? Interesting thing that might have shown up, you might have questions on, is you notice I'm using a double arrow in between here. So if we take a look at that bottom reaction, we could go through and specify what's happening with that bottom one. SO3 - 2 can now act as a base. Could it act as an acid? Can SO3 - 2 act as an acid? Why not? It needs to have a hydrogen. There's no hydrogen there for it to lose. Okay? So if we run that reaction now, we can lose a hydrogen from our H3O+. We can add a hydrogen to our base. And what do we end up making? Interesting. Same thing that we started with in the previous reaction. What does that double-headed arrow mean? Goes both directions. So when we looked at reactions so far, we said they go one direction and one direction only. In reality, no reaction goes only one direction. They go both directions. So as soon as I make some product, what happens? Those products are now reactants, and they go the opposite direction. Okay? Kind of a confusing concept. Okay? In fact, it's an extremely confusing concept. So confusing that we devote an entire semester of general chemistry to it. That's 152, is just looking at this concept. That concept carries a very particular name. That name is known as equilibrium. We're about to look at that in the slide. Next slide. Next definition we need to hit, though, is this idea of conjugate partners. Okay? So what we can go through and do within that reaction is start to compare things across the reaction arrow and say, these two things are related to each other. And we will call them conjugate partners. The most horrible example that I can think of, we can look at conjugal visits. Okay? You're looking at bringing partners near each other in, what was it, prison, right? Okay? Not that I would know. Well, maybe not yet. Okay? Conjugate base. So we would now apply and look at our reaction. We'll call the SO3 minus 2 in that first reaction the conjugate base. It's conjugate because it's partnered with the HSO3 minus. Why is it labeled as a conjugate base, though? It came from the acid. What would it act as to do the reverse reaction? A base. Okay? So what we're looking at with these conjugate partners is comparing across the reaction what things can act as a base, what is it most similar to. It's now a conjugate partner. Okay? And those names will change. Really hate this definition, but it definitely shows up, I think, on the practice exam. If you're asked to identify the conjugate acid in this equation, what species or species is your conjugate acid? Your conjugate acid is a base?
Well, it'll be that, the base turned into that.
Okay, so we can go with H3O plus, that's labeled as a conjugate acid. Is there no other conjugate acid? HSO3 minus, for some reason, is being labeled as a conjugate acid. It's definitely something I need to bring up with the department because I think that's a load. Okay. So realize when you're being asked to identify your conjugate base or your conjugate acid, really what they're asking you is define all of the species that are bases. Because within the reaction, this base, H2O, is a base in this reaction. But if we look at the reverse reaction, what is it now? It's also a conjugate base. Okay? I know that's a bit confusing, but be aware that conjugate applies to both sides of the equation. Okay? And after the exam, I can tell you I told you so. I didn't say that out loud. That double arrow, equilibrium. Okay? We're saying all reactions are reversible. They go backwards and forwards. What makes this interesting is we hit this concept known as Le Chatelier's principle. Okay? Reactions will always push to reach equilibrium. Okay? Which is kind of an interesting concept that we've addressed before. Everything strives for neutrality. Okay? If we go forward, well, what's the opposite of forward? Backwards. We're striving for that point where our forward and our reverse match. What makes that a little bit tricky is that doesn't mean that our concentrations are equal on both sides. It just means that the rate of the forward reaction equals the rate of the reverse. Okay? Why is that important to Le Chatelier? Well, what happens if I reach equilibrium? So now the reaction is happy. All of the concentrations are exactly where they need to be. Everything is in perfect balance. Now I throw in a bunch of H3O plus into that equation. What does the reaction do? It needs to achieve balance. So what does it do to achieve that balance? Okay. Shown another way, if we take a seesaw, we've now achieved our balance. What happens if I throw in a bunch of H3O plus? It's not balanced. How do I make it balanced? What has to happen? What's that? We can't put H3O plus on the other side because everything is in the same solution. I need to get rid of some of that H3O plus, but the only way I can get rid of it is if H3O plus acts as a reactant to make the left side of the equation, which means what we're going to do to balance is take a little bit of this section and put it over here. And it now balances out. So if I add reactant, what does the reaction do? It's going to shift to make products to get rid of that reactant concentration. If I add products, what's it going to do? Make reactants so I can get rid of that excess. Okay, so you can look at it as kind of a seesaw. That's ultimately what the Chatelier's principle is looking at, is trying to find that balance between those. Okay? I know it's time, and I'm just going to tap here real quickly. Strong acids, strong bases. Electrolytes. This is kind of an important definition. I'll just mention this because I think it is pretty quick. What are we looking at with electrolytes? Electro sounds like electricity. All an electrolyte is that when we put those into water, we get electric current, okay, or that we can pass electric current through it. Okay? Electrons are highly unstable, so what do we need to help stabilize those electrons? We need other ions. Okay? So an electrolyte is just something that when it hits water, it dissociates into ions. So anything that's aqueous, anything ionic, those will push into those ion formats, and you should be good to go. Right? I might post, in fact, I will have to post probably an extra 10, 15 minutes just to get through some of the other slides. It's not that much more, so it shouldn't be that big of a deal. Small concepts. Okay?